And here's what we were talking about previously. We were talking about this idea of an accumulating quantity. And remember, all it means when you say a quantity is an accumulating quantity is that the whole is the sum of the parts, like mass and area. And you can imagine, it's a fun little exercise to think of other quantities that in fact are accumulating quantities. And here's a hint. Anything you've ever computed with an integral is an accumulating quantity. Right? So, that said, perimeter is not an accumulating quantity, right? The perimeter of the whole is not the same as the sum of the perimeters of the parts, right? So easy counterexample. So my point being here, just because you write something down doesn't mean that it's necessarily going to have this fabulous feature of being an accumulating quantity. So it's something that we have to demonstrate, not take for granted. Okay, so again, we've already talked about this, so I'm going to go quickly through it, but the big idea of this point is that if you have an accumulating quantity, you can think of it as behaving kind of like stuff of some sort. It might not be stuff, and you don't have to think of it that way, I suppose. But you can, and it is very helpful to think of it as being kind of like a physical stuff in the sense that it can be thought of as being distributed over the area. Nothing goes wrong. The whole is the sum of the parts, and so it just works, right? It's an option, and ends up being a very cool option. Because, among other things, it allows you to talk about density. Now, this idea of mass density is a yawn, right? This is something y'all have seen for a very long time, probably. You've probably been somewhat aware of the variation on this idea of population density. It's, stuff per unit size. It's kind of a broad stroke idea of what a density is. And the number of people is a kind of a stuff in some sense, right? Where it starts to get a little weird is when you want to talk about work density. Again, work is not something that we think of as a kind of a stuff, but it's an accumulating quantity. So stuff or not, you can think of it as a stuff. It behaves like stuff. And so, among other things, you can talk about its density, work per unit area. It's kind of a weird idea, right? Something you have to digest a little bit. But any accumulating quantity, you can do this. And once you have these observations made, then it's a hop, skip, and a jump to point out that in the same way that you can compute mass as an integral of mass density, you can compute any accumulating quantity as an integral of its corresponding density. So, for example, work, again, we don't think of it as a stuff, but it is an accumulating quantity. The whole is the sum of the parts. And on any given little piece, we do have this idea of a density, namely, stuff being stuff per unit area times area. And boom, integral, something to compute. Okay. All right. So this is about where we left off before. I think it's kind of a cool observation that really, and I've already said this, but pretty much any integral you can think of as being just a kind of an implementation of these broad ideas. But this is a broadening of how we tend to think of these ideas. Okay. For whatever it's worth, sometimes the resulting theorems I like to call by these different names. The accumulation theorem term, because of course it all hinges on the quantity in fact having this feature of accumulation. The density theorem term, because, well, it ultimately ends up being an integral of a density. So you're going to hear me use both of those terms probably throughout the rest of this semester. And then last observation I'll make is that there's nothing really particularly key about the fact that we talked about quantities accumulating over areas. Quantities can accumulate over volumes also, right? Where the whole is the sum of the parts, and if you divide up the volume into two smaller pieces of volume, or however many little pieces of volume, that the whole is the sum of the parts. Then again, you get a corresponding theorem. All the same ideas. And then likewise, one-dimensionally, right? Same basic ideas, now lengths instead of areas or volumes. Okay. All right, so there is a particularly surprising example of an accumulating quantity. It's going to take me a minute to get to where we can actually define it. But it's going to end up being extremely important. And here it is. Actually, well, not quite. Here comes the development that will lead to what this accumulating quantity is. Before I do that, I do have to define what I mean by boundary. Now, we've used the term boundary before. You all have heard the term boundary. It's a pretty reasonable idea. Boundary is the border between where your set is and where your set isn't, right? Or it's the edge of your set. Take your pick, right? Different ways to think about it. The problem is that henceforth, we're going to have to think of boundary as being oriented. It turns out, and you're going to see why in a couple seconds, it turns out that when you think of boundaries as being oriented, and in particular, oriented according to a very specific convention, you got to orient appropriately according to a specific convention. When you do, awesome things happen. Amazing, surprising, shocking results come out. So the following is going to seem pretty arbitrary, and it kind of is. But awesomeness is going to follow. So here we go. Here's the rule. If you have some region, and I've drawn here just part of some region. I didn't want to draw the whole thing. So just some part of the region. There's a corresponding boundary curve, of course. Here's the boundary curve. And when you're on the boundary curve, of course, there are two different ways that you can move along the boundary curve. I could move that way along the boundary curve, or I could move that way along the boundary curve. Right? So which one should you do? When we say the word boundary, with the understanding that it's to be oriented, the correct direction to go is whichever direction that puts the region on your left. And now, geometric appeal, imagine being on that purple boundary curve and moving in the dark blue direction. As you walk in that dark blue direction, the region whose boundary you're talking about is indeed on your left. Does everybody see that? Everybody see how the geometry works out there? Okay. All right. Okay, and then likewise, if I were to look at a different part of the region, so let's look at this. This is just a different diagram here. The boundary is a curve that's about like this. Now again, which way do we go? Two different ways we could go. It's not as simple as always to the right or always up or anything like that. You go in whichever direction puts the region on your left. Now, if you make the mistake of going this way, then notice the region is not on your left. Now the region's on your right. That's not how it works. That's not the convention. The convention, again, always walk in whichever direction would put the region on your left. Is that cool? Is everybody happy? All right. Okay. Arbitrary, weird, seemingly pulled out of thin air. By the way, for whatever it's worth, there's nothing magic about left. If the mathematical community had decided 200 years ago, when these ideas, I think, were first kind of coming out, let's do it the other way. No problem. Right? We would have slightly different theorems that would look a little bit different. The convention obviously would be different, but it would still work, right? So I cannot emphasize enough. This is a totally arbitrary choice. There's nothing magic about left. The thing is, this is a convention that has been agreed upon and pretty universally settled, and so this is not optional, right? It is arbitrary. I should say it was arbitrary. Now it is a standard. All right, so it is important. Okay, oversimplification is to think that if you have a region and you look at the boundary, wouldn't it be the case that the direction you go that puts the region on your left, isn't that always counterclockwise? Right? mean, you look at the picture, it kind of feels like that ought to, shouldn't that always be the case? Not quite. If you're going around the outside part of the boundary, yeah, I suppose. But here's the thing. Not every region is what we call simply connected. So you imagine this region here that I have, again, I'm just going to kind of vaguely, but that region there that I have in gray, its boundary has 3 different chunks. Right? And if I look at these 3 different chunks and ask, okay, well, what's the orientation on each one of these chunks? And let's think in particular about this chunk right here. Well, which direction do I go? I go that way because that puts the region whose boundary we're talking about on my left. And notice that would have me going clockwise, not counterclockwise. Right, so you can't oversimplify this and just say, oh yeah, counterclockwise is always the rule. There's an asterisk on that. That's only if you're going around the outside part of the boundary. You got to be really careful about that. So please don't oversimplify the convention. Okay, and with all of this said, here's the new accumulating quantity. It's really hard to see this coming. And in fact, when you first write this down, it seems wrong. But I claim that boundary circulation is an accumulating quantity. And we're going to see why momentarily. Ultimately, no big deal, but it is surprising. And the question we're going to have to ask, keep in mind, is the whole the sum of the parts? So, for example, if I look at this left side of this region, and if I look at its, boundary circulation, now keep in mind, boundary means you're going a particular direction. Region on your left and all that. So, boundary circulation of D1 would be this dark green curve. Okay. Now let's look at the region on the right. Talk about its boundary circulation. Okay, well again, boundary, I have to move in such a way that the region is on my left. So I'm going this way. Like so. And now we think about the whole. And for the whole, which is messy to leave there, I go around again with the region on my left. And now we ask, is the green integral plus the blue integral equal to the purple integral? And the very first thing that might occur to you is we've got the same problem we did when we looked at perimeter. Perimeters don't work. Perimeter, the whole is not the sum of the parts. With perimeter, you've got extra sort of perimeter happening on this cut edge in the middle, and it just doesn't work, right? But this beautiful thing happens here, that because we're talking not about perimeter, I'm not talking about the length of the boundary, I'm talking about circulation of some given vector field around the boundary. That circulation has an orientation to it. We're not talking about intrinsically positive things that can't cancel. We're talking about signed things, right? And here's how the cancellation works. It's actually pretty believable, I think, that all of this, the green cancels with the purple, and then over here the blue cancels with the purple. All of that's pretty satisfying, so let me just go ahead and erase all that part. Note then that all that's left, the only thing that hasn't canceled, the only discrepancy, the only thing keeping this from working is that I've got line integral on that red edge twice, but twice with opposite orientations. Don't forget, when you orient oppositely, then you get the opposite, you get the negative value. So that green integral and that blue integral on that red edge, they cancel in a puff of smoke. And therefore, there is no discrepancy. And the whole is the sum of the parts. And this is an accumulating quantity. Boundary circulation is an accumulating quantity and powerful result, because keep in mind, whenever you have an accumulating quantity, weird though it may seem, you can think of that as stuff distributed over the area with a corresponding density which then you can integrate to make a theorem. And it's satisfying when you do it with math. It's a little weird, but kind of okay when you do it with work. We're about to do that now with boundary circulation. And just a real quick preview, what we're going to find is that is going to directly give us what's called Green's theorem, and we will pick up with that next week on Tuesday. See y'all later. Have a good one.